Alright, so there's a little question for you guys to start with. You know this one. Is it a graph? This is, well, it's not labeled. This is something here, and this is something here. Any guesses what that is? It's just completely random. Oh, so. What do you think about that? So I should say, so next week I'm away on Wednesday and Thursday. I have a conference on Wednesday, so I need to, it's possible we will do something Friday, figure that out. Otherwise I'll re-establish that Thursday lecture in some way, so I'll figure that out. So no office hours next week, and the assignment we'll have will be due the week after. Sorry to let you know that I'm having an assignment. You can pretend, I mean, you just do it. Any guesses what this is? So it goes, actually, so it's mostly increasing, it goes down here a little bit. What's this? This is years. Some of you guys. Population? There's something bad happening here, right? That would be the big
Chronic plague, you can see it.
It was pretty bad. I mean, it's true.
Is it the number of religions?
Number of religions. That would be a great thing to try. Religion, the size of religions must have a pretty good distribution as well. Right? If you get more sex, you know, the person who thinks he's Jesus, that's a religion. And there are lots of those. Number of books. So all right, so this is 3000 BC. Struggling.
Okay, I didn't write that.
Something didn't. Whatever happened back here, just knocked it out of the park. Right? And then, if this is good, and if up is good, and now we've taken off for a second. Any guesses? More guesses? It's a human thing. It's something we did. All right. So it's the height of the tallest structure. So these are the pyramids. I have a representative from Egypt, so so we really struggled for a long time to stack things up until we get better. I think this is a story where a spire fell off. Somebody, Europeans got a little crazy with some of the cathedrals and so on, and they lost a few in some storms, and then of course it deserved recently. So there you go. That's just you can make all sorts of big graphs like that. That's it. I think I have it. Yeah, there you go. So there's the list. Right. England had it, then it fell over. Estonia in front for a while. Germany. The Eiffel Tower, which was only supposed to be up for a year. So let's just is that right? So we're good at this stuff. Just gonna knock it out, take it down. Stop up. And now it is the same. Okay. Complicated relationships. Alright. That's just it. So I have a list of things to do. So I was going to talk about some of the so I had this idea of touching on the fundamentals as we go through, so I wanted to mention a few slides on statistical mechanics, which is a vast field, but I'll give you a few slides on that. Tell you what that is. I want to talk about Benford's law, which is a funny little thing, and then we'll get on to this robustness business. Which will have a theme, so this is episode 8. That'll have a little thing to it. We'll get out of it. Well, actually, I was going to say we'll get out of the 980s, because the highlight didn't want to do that. So, but this one. Cool, but let's see. So, alright, so this is statistical mechanics. Just wanted to say a few things about this. So this is the field that I was immersed in, kind of without my knowledge of it, as I went through undergrad. I just thought everyone in the world did this, right? But I was sort of a specialty at Melbourne Uni in math and physics. I love to count things, basically. So this is Philip Paul, and I've mentioned this book, Critical Mass. It's still a very good book to read. It's from maybe 10 years ago. And so he's having this go a little bit of complexity saying, really what people are running around talking about is actually been around for a long time. So main things in complexity theory have been studied for more than 100 years. It's true, so you go back to Maxwell, Boltzmann, all these guys. And there's a very interesting twist to this. by physicists who evolved a toolkit of concepts and techniques to which complexity studies have barely added new items. Now, yeah, that's sort of still true. Right? I mean, what's happened is we've been able to describe a lot more things. This data has come online, particularly networks, which is a big topic coming up. And that's really, what is it? It's only 15 years. 15 years since that opened up and exploded. But a lot of statistical mechanical tools apply beautifully to a very large class of random networks to figure out all sorts of things. Okay, so let me tell you what it is. So basically, yeah, so science of collective behavior, which sounds great. So we might think we can do this with people. You see some physicists get a little carried away. But it has this essence that I've talked about earlier on, micro to macro. So there's some simple rules for how agents interact, and then you have some collective phenomena that is noticeably different, right? This is the story of emergence that we've talked about. It's different, not just quantitatively or in size, but qualitatively. You're getting behavior out that's fundamentally. So we talked about, say, water molecules hanging out, getting some thunderstorm, having hurricanes and so on. There isn't a hurricane, so represented in any one water molecule. Or a broomstick or whatever is floating around there. Okay, so stat mech. So I'm just going to give you a tiny little introduction to it, just a little glimpse of one of the most famous things. If you can see this very well. So this is a model from the 30s, I believe. That's right. So Ising was a graduate student. He said, "I'm going to make a model of magnets." Right? So magnets are good things and useful for all sorts of stuff. And then so he made up this ridiculous model. But it's been a great source of interest for a long time. So imagine here's a little one-dimensional version where you have a discrete world, and so you have these little spins sitting at each point, and they're spaced evenly, and they spin up. So they're all tiny magnets. So this is counter to what I was just saying, I suppose. This is a world where tiny magnets make up big magnets. This is a sort of homunculus like we have a little tiny magnet. Now it's true, of course, we do have these little spins, so this is an okay thing. And so we'll say they can either be plus or minus, right? Up or down. And they like to be pointing in the same direction, just like experience with normal magnets. So, but that is balanced by the overall temperature, or if there's an ambient field. But let's say there's no ambient field. The temperature, as that goes up, you care less and less about your immediate neighbors. And the simplest model is to just have each spin coupled to its immediate neighbor. You can imagine the coupling going further out, so this guy cares about what's next to him, and then so on and so on. They're not actually done this. But anyway, and here's a 2D version, so I'll have more to say about that in a second. You can put it on all sorts of lattices, so you can see where the math goes berserk, and people push all sorts of fun papers about things like hexagonal lattices, which are probably, sometimes it's a good thing to do, sometimes it's just having fun. So they're arranged on a lattice, some kind of lattice. The spins like to align with each other. The temperature will break this alignment. And this is just the base, right? It's the fruit fly of stat mech. It's just the sort of essential model that people play with. Now, completely made up, but it turns out to have very real properties that match real phenomena very nicely. So, this is more obvious. But if you see, so this story here is, so temperature is going this way, so this is zero temperature here, so this is Kelvin is going this way. This is the overall magnetism. So you imagine you have, so let's imagine this guy. We have this big two-dimensional plane of spins. And as we drop the temperature, so as the temperature run out very high, they're up and down, they don't really care, right? They're not feeling it from each other. As the temperature drops down, that effect is dropping, and they become more attuned to each other. So what you'll see is either, so this is a net magnetic field up, net magnetic field down. Either it will go this way or this way, depending on just chance. Right? So as you drop the temperature down, local spins start to align with each other, and then just by chance you get big enough groups, and eventually they'll all be pointing one way. Right? So this is a very low entropy state. We talked about entropy earlier. This is the lowest entropy state. all pointing up or all pointing down, and you have a very strong magnetic field. So, with nice math, you can get out this bifurcation here, and you can see, depending on the systems, there are many different types of systems that have this. So this is a phase transition. This is the emblematic phase transition, right? So there's no net magnetic field here. It's positive magnetic. You're out here, you look at this chunk of metal or whatever it is, and you can't measure anything magnetic about it. Drop the temperature down, suddenly there's an overall macroscopic field coming out. So this is that's a big deal. So the term that came to be used for these phase transitions, so you call this a continuous, a different term, but a continuous phase transition because, yeah, it's smooth, right? So there's no abrupt jump here. There's an abrupt jump in the derivative of this thing, and higher order derivatives. Sometimes, of course, in some things you can have an abrupt jump, but that's a first order phase transition or right? So we go from one place to another, and of course, once we're talking about all sorts of more complex real systems, that kind of behavior is very possible, right? So, country is stable, country is in disaster, right? Or, no. We'll get to that later on. We'll touch on some ideas of not how to make countries better, but just sort of try to get how that can happen. How you can sort of have things going on well, there's a neutrality to the whole situation, macroscopically it all looks okay, it's nothing, there's no one way or the other, and then it can all explode, right? What you see, so imagine now, if you look at the size of the little clumps that are all pointing in the same way. Okay, so right out here, there's randomness, so the sizes are all different. This is a big thing. In stat mech, so you might clump all of the positives together like this, and I'll try to run some visualizations and fail, but we'll try to do that. So it'll be like this. As you turn up so we'll increase the temperature this way, and these little clumps might get smaller. Right? And it's hard for humans to draw randomness, so we're struggling. And as we go down this way, so this is temperature, as we go down this way, we get larger blobs. So there might be little ones like this, some little clumps. So right at this phase transition, at this critical point, it depends on what you're doing. So this could be water going to ice, for example. Classic phase transitions, sort of like gas and forth. You get blobs of all sizes. So over here you have a macroscopic, you can see it. By macroscopic you can see, if you can see the system, you can see the spins that are all pointing up. If you color them up, one color blue and the other color red, you can see a big lump of blue. Here you can't see it, it's all static. But at this point, you see these clumps of all sizes. So this is a point we'll come back to with the robustness story. There's a very special point here where the distribution of sizes of groups has a parallel size distribution. We love those things. We think they happen everywhere. Okay, but they only happen at this critical point in all these stat mech typologies. So what we'll come to later is this idea of maybe some self-organized criticality. So many of these systems that we see that have powers all the time, so we talk about language and wealth and all sorts of things, and we have this model, Simon's model, that seems to be the best sort of basic model at the moment. Another point of view has been to say, well, somehow these systems have organized themselves to get to this point. Somehow language is organized itself. This is adjacent to the Benford story and Simon's story. This is another idea. Judah Per-Bach, whose book fame is may have had a few books, but he has one book which is just called How Nature Works. So he's a physicist just going to say, now this, I will explain everything to you people in other fields. It's not right, if I need to say it. Okay, so there's this idea that somehow by tuning you end up at this point. Somehow there's a self-tuning in the system. So this is self-organized criticality, which sounds fantastic. It's suck. Criticality has a very special word in meaning in physics. Bring it back out, and it sounds very cool. It's very exciting. That's what happens in the super. Okay, so that's a big deal here. But it's only at this point. Once you come to this side, now you have a giant piece, and then little guys, and out here they're all little guys. You don't see those distributions. Okay, so let me see if I get this guy to run. this is there are various little models online. Slither, there you go. Wow. Just keep it running. So we'll start with, so there's the initial state. So these are up and down. So depending on the temperature, so here's the critical point. So you see they're starting to coalesce. And over time, there's going to be a winner, but it's a bit of a fight. Right? So this is a two-dimensional magnet on a bagel. It's important. Pretty sure it wraps around. Yeah, right, so this little blob joins over this little blob over here, right, so it wraps this way, and we haven't done it. Or a bagel if you want. Slightly more healthy if you're gluten intolerant, it's a disaster. So let's just call it a platonic torus. Okay. Okay, so that's going to go, right, so you can see what's in that. So then you can, and if you warm it up again, it's just going to say, right, so now there's no, they're all small groups, they're small sizes, one size of a small, we get to this guy, and it gets tricky. That's going to be really cold. Right, so this is just an emblematic model, very well studied. I'll say more about this later on. So one dimension, it's easy to study, it's easy to figure this out, to solve the thing analytically, given a particular statement of the model, which is that you have some preference to be like the spin's right next to you. Not nowhere anyone wants to be on that. That becomes more complicated. That turns out to be solvable. It turns out that the phase transition is at 0 temperature, so there's nothing interesting. You don't see what's interesting, you don't see the bifurcation. 2 dimensions is where you start to see something interesting. And that was very hard to solve mathematically. One side to solve this, the reason I think is that applied mathematicians and mathematicians rejoiced, and no one the real world. But the idea is, that's what we're doing. Okay, slip. That's what we're doing. Ready for I know, you're all the world. I think we do something fast. Okay. Pretty bold statements about this level, I'm not sure. Right, let's let that go. That can go back. We'll see if, so who's winning this? So there's all these little fights going on at the boundaries here. So what people have done, of course, is say, okay, this is one half of Europe in the Second World War, and this is the other. There's direct mapping, or this is left wing and right wing. This is opinion dynamics. We'll put it on a network. Let's put it on a network. Everyone has a little up and down spin. And of course, you just wholesale use the tool, or use the model that we had for a magnet, which itself was a ridiculous model for a magnet. It's totally complete total. That's so you can't be too upset about it in some ways because it's already sort of. But we need silly models that draw on social behavior. And Schelling's model is a good example. Yeah, so I think what you're going to see, these little promontories are in trouble. That should get eaten up. This one's going to get eaten up. So there are boundary problems. All right. Okay. Good. Stat. Let's say a few more things about stat here. Okay. So many different other areas you can think about. This is liquids. So we've got gaseous phase out here. This is temperature, pressure, liquid. So there are different kinds of states. So that's what we're talking about, macro states. Of course, the molecules involved are still the same things. They're just behaving collectively in different ways. So this is very, so as I said, qualitatively distinct macro states. So this is so you can think of traffic as this kind of sort of phase diagrams of traffic, for example. So free-flowing traffic will be in some part of the phase diagram, and then across the border, and then there'll be congestion, traffic jams. So this is a very useful thing so I mentioned traffic. There's also these ridiculous things called oscillons. Snowflakes have a similar story. So this was on the front cover of Nature in 1996, and it's based on a very famous experiment by Faraday, Michael Faraday, and others, I suppose, at the time, where they just looking at everything they could, I suppose, so they have a pan of water and just shake it up and down. So you have some little oscillating thing that shakes it up and down, and then you see interesting patterns. And so the fluid dynamics is a very difficult area. We've done incredibly well with it. You can see square patterns, hexagonal patterns, and you can argue based on the amplitude and the frequency which states you might see analytically. So it's an interesting thing. And of course, we care about how things jiggle up and down. It could be fuel, it could be milk, whatever it is. The granular media we care about, right, because food, right? Food. Granular media is, and that's what these are. These are tiny little ball bearings. So this experiment, all little ball bearings, and they're just being shaken up and down in the same way as Faraday. So the idea was, well, granular media, different fluids, sometimes like fluids, sometimes not. What happens in this classic experiment if we do it with ball bearings? And so you get these, you can actually get these little isolated pulses that just live by themselves. And you can manufacture this in fluids, so some maniacs later on did this. But it's very, it's very unusual. So you'll see, this will sit there happily, and it depends, you have to have everything set up, it'll sit there happily going up and down. So this one's out of phase with this one. All of it. Brentwood. So this is Swinney, this is down in Texas. And so in fact, so here's the frequency, I think that's amplitude, right? So frequency and amplitude. So you see a flat layer here when it's a low amplitude, regardless of frequency, it's all going up and down the same thing. It's just making it. It's like a big trampoline with lots of people on it. You get square patterns here, squares and then sometimes stripes. I don't think they're hexagons in this one. So you can see there's a lot of sitting there, you're a graduate student, you go through and you dial the knobs and you look at it for one time and you say, okay, what's this? And you get this phase border, oscillons. And then there was a big game to do this analog. Silos, for example, quite famously, so granular media. I grew up on a farm, so some bad stories that I know about because of this. You fill your silo up with grain, and what happens if it was fluids? If it was a pure fluid, the pressure would just increase linearly on the bottom, and we know what to do about that. And the pressure on the outside would be manageable. But you get force chains in, so it's wheat or something like that. You get these force chains, so the pressure is being distributed in weird, branching network type ways, and actually starts to really get into the outsides of the silo. So tall enough, thin enough, you get silos that explode. Right? Another problem is you start to get. I'll spend the rest of the time talking about farms. Okay, so you bring some of the grain out, because it's mostly what you want to do. You put it in your truck and you drive it away. It's taken away the railroads. Okay. But it doesn't flow out properly. If it was fluids, it would just flow out perfectly. But it doesn't flow out properly sometimes, and you get these cavities sitting there. And then, of course, you go and probably stick because you're a farmer. You shouldn't do that. And then it all collapses, right? So, so you have to be really careful with this stuff. But so much what we move around is food, rice, wheat, granular form. So, good problem. Okay. So that's still going on. That's a big area of research, and it's hard. This is for bacteria growing. Also, so as I said, you can find everything. This is the nutrient supply moving this way, the initial amount of it, so the amount of wetness, and you get qualitatively different structures. Bacteria also. Now, I touched on this. Okay, so it's in the 20s. So the 1D version of the Ising model is simple. This is just something I want to say about these kinds of models in general. Just touch on it. It's a huge, huge area. 2D is very hard, so it's on celebrate. It's crazy and figures it out. Really, really hard. And 3D is impossible. No one's done this. No one can do this. It's impossible. So you just add a three-dimensional Ising model, just care about your local neighbors, 6 of them. Can't do it. And I think this way, at 40 and up, it becomes simple. I don't know if the 4 dimensions is right, but usually this is the case. 1D is usually easy and not exciting. Right? 2D, sometimes you can do it, but usually interesting things start to happen at that point. You get this nice phase transition. 3D, which of course unfortunately is where we live, is often extremely hard. But there'll be some what we call upper critical dimension, 4, 5, 6, and sometimes it's fractional because we're insane, above which it's really easy to solve, and everything's kind of the same. So it's basically, if you get to 20 dimensions, for example, there are so many different ways you can go that everything starts to be connected to everything else. So it's what we call a mean field type situation where instead of just worrying about your neighbors, you think about what everyone else is doing. Which is a great kind of model. I mean, that's a good model. That's a very good basic model of say media's influence on people. All the average votes or inputs of everyone else somehow being registered in your head. It's much more complicated. All right. So here's the last piece I want to say about this. So we go back to Maxwell and all these crazy people thinking about gases. Right? And so this is the world of mechanical thinking, physics, and you want to think about your little atom hitting this other guy and bounce off each other. That's kind of the problem to solve. And of course, there are lots of molecules and atoms to think about hitting each other. So that's going to be tough. This is a long time before computers, and even still, we can't. Tiny little patch of air is something we can simulate in some reasonably full way. They were actually inspired though by things like actuarial claims. So people were using statistics to describe the behavior of people. How many people were going to die next year, being hit to death by a horse or something, or how many were going to have this sickness fall upon them. Or possibly good things as well. But we got to this point where we count these things up and estimate what would happen next year, which is a bit upsetting for some because that's something about God and destiny and so on. Okay, but there was this idea of randomness. Anyway, so their inspiration was from that. They thought, all right, well let's imagine these atoms are not, we don't kind of think of them as hard little fixed things bouncing off each other. We'll have a much more statistical think of them probabilistically, behaving probabilistically, locally, and then we get up into macro stories, just like the perfect gas. So then, oddly, you have the physicists of the last 10, 15 years have gone back to use these techniques to study heat and all sorts of other things. So that's a funny little it's pretty cool analysis and stuff. Okay, good. Alright, so that's just a very brief piece about stat mech because we didn't know if you were listening. So it's key things, it's the micro to macro story, it's inherently probabilistic, this idea of phase transitions. What we'll go to, and traditionally a very good way to learn this, especially in math, is percolation models. Right? So academics are obsessed by coffee, fueled by coffee, basically, right? So, or tea. A few errors human beings drink tea. So, percolation. Great problem as well, good fun problem. But basically, you do this, it's very simple. You just say, okay, I have a grid, and then with probability P, you color in a square. If you go through each of them, you flip a coin that's biased, P minus P, do this, and then depending on this value of P, you will, so if P is 1, you color the whole thing in, and if 0 is nothing for it. And the idea is you connect all of the ones that are colored into groups. Right? And so if P is large enough, you'll be able to get a big component that connects from one side to the other. So this is exactly the same story as what I was talking about with the Ising model. Green is a large one. Okay. It's going to be it. Yeah. So you should not make an analogy to politics. All right. So, but again, there's a critical point at which you get a size that's just a thin, tendrily thing, a cluster that's thin and tendrily and just reaches across. practical dimension, it's not really cool. Once you make P go a little higher than that, you fill in a few more things, you can see it. You can stand back from a big one that's 10 billion by 10 billion, and you can see that filled in percolation cluster. The idea is it percolates. So people worry about this for oil, actually, getting oil out of the ground. So big oil is all over that for a while. But so that's percolation. It's a nice way to do it. But there's a this is of course a lattice. That's a reason you think about 3 dimensions. That's a reasonable model of the Earth. But we'll talk about networks. We can do all this very nicely. So we'll get all those things, phase transitions and so on. Okay. Good. That's good. So I'm going to throw this in Benford's law. It's another little parallel story. Oh yeah, out of the hashtag. It's built into the code. Very exciting. So Benford's law, it's just a few little things. So, kind of a famous law. It's been around for a long time. I don't know if you've anyone heard of this thing? Yeah? Yeah. Yeah. All right. So it's probably the first digit. So you have a bunch of numbers, and you look at simply the first digit of those numbers. It's a weird thing to do, right? So I'll show you a few examples. But say you take so a good one is tax returns, right? So you take a whole bunch of tax returns, and you just pull out all the numbers that are in those tax returns that people make. The ones that are set in there, but the ones that people make, they're dollars. Just you put them all on a big list, and then you count how many start with the number 1. And it's a certain thing to do. And then you count how many start with number 2, and 3, and 4, up to 9, so base 10, and then make a little histogram. And it turns out it follows this law. So approximately, and not for everything, but you see this for a number of examples. So it's 1 plus 1 over d. We'll think about this in a little bit. But 1 plus 1 over d, so it's decreasing. So for 1, it's log of 2. But it's going up to log of 1 plus 1 over 9. So it's decreasing. So there's less chance of finding something that starts with a 9. So again, this is something that, for us trying to make up numbers, you try to make up your tax return, and you've got enough numbers in it, you won't do this. But it's very interesting. Of course, we know that if you cheat it, you won't do this. So that turns out you get 30%, first digit will be 1, less than 5% will be 9, so it's a big difference. And this was first noted by Simon Newcomb in 1881, and I think it was from looking at books of logarithms. You start to see that the pages, the one pages were thumbed in different ways. So the book was being worn in a different way, not uniform. So, wrote a little paper about it, kind of forgotten. This fellow Benford, a physicist, discovered as well, and we ended up being called Benford's law in the great tradition of Newcomb often gets mentioned, just as we've done here. Okay, so let's have a look at this. So you see for a few things. I said tax returns, utility bills, fundamental constants. You just group all those guys together. Death rates, funny numbers in newspapers. Just pull them. Not everything. And so now there's a suite of reasons for why a particular collection of numbers will give rise to this. I'll give you one example, but there are many others. And so here's an example. So people use this as a. No one's going to believe it if you say, oh, it doesn't conform to BEM. That's probably. It should look like this 1 plus 1 over d. You put that on CNN or something. Show your peak. But insurance companies will look at it. And tax guys, definitely. This is good. So this is for real numbers. So this is the numbers from newspapers, numbers from the census, numbers from the government. All of them doing pretty well, and this is the exact version here. So this fellow Hill did a bunch of work on it recently. So it's not. You think it might be good. This is physical constants of the natural constants. So this is big stuff. So not bad. Populations of countries. So here's just a tiny little thing we can think about here. All right, so it works in any base, which is also strange. The base doesn't matter, right? So binary is a little funny. The base doesn't. Once you do base 3, 4, 5, you can turn that. You can take your numbers, turn them into a different base, and you'll have another little log, which will be log base b. All right, so let's look at this. Okay, it's 1 plus 1 over d, which is d plus 1 over d. We'll just put those guys together. And we know all about our logs, so it's log of d plus 1 minus log of d. So probably the first digit is 1, is the log of 2 minus the log of 1. So I'll show this on some other slides, but if you think, okay, well let's make a log scale here. Right, let's put 1 here, 2, fail, 3, and 10 here. And if we draw a line across here for our probability distribution, this piece here, this is some constant here, this area is proportional to log of our base 2 minus log of base 1. And this area is proportional to log of 3 minus log base 2. Right, so we're talking about a uniform distribution as a function of the natural log of these digits. That's the way to see it. Okay. All right, so if the numbers are distributed uniformly in log space, then we're good. So that means we have this, and the probability, let's do natural. I'm just doing natural log. So, but again, we know we can convert this. That's why the base doesn't matter. Okay. So think of this. So with P of log of x, d log of x, if we're in that space, it's proportional to 1, right? It's a uniform distribution. And if we do DL, if we play around with this guy, it's just you differentiate that, we get x to the minus 1 dx. So that's a little power. So that's the connection. A little power that's popping up. For extreme 1, we see it again, and we have this gamma of 1. Again, there are other ways to get to this. And I have on this slide, again, this is actually just taking a quick peek. When I first started this, tiny little entry on this, a lot. So if you had a distribution of numbers that's spread out across log space like this, and it's somewhat flat in the middle, this is going to give you something that conforms roughly to the. So you can see here, here's the chance of getting a 1. Chance of getting a 1, chance of getting a 1, this is the chance of getting a 9, it's much smaller, but it's uniform across here, so that area is what's being associated with a 1. So it's 100 up to 199, 1,000 up to 1999. So if you have a more distribution, certainly not uniform in any way in log space, then you get these very different. So, I think that's very cool. And it's been observed. I don't know what you would, but with themselves, it's so excited about it, I should say. That's why you should be very careful when you write down numbers. One other reason. Okay. Not very good thing. Okay, Benford. So just a little extra power. Hang it in there. Speed it up. Just getting much. Good. Good. List of things to do. Robustness. Excellent. So this is a great story. This is good, complicated stuff. More arguing between people. That's great. Somehow we're going to understand this little guy here. This is to do with forest fires. And I mentioned this the other day, but these are 4 different, if you like, designs for forest breaks in a fire. So the white here represents trees, the black represents where trees are not, it was a fire break, and these are different designs in response to a lightning strike path. And this one's going to be the most robust in the sense that because the lightnings, I'll show you a picture of this, I just happen to do that. There are more lightning strikes over here. I mean, less lightning strikes over here, so you're right, you're going to give up something to reinforce this section. But if it goes wrong, if you do get it, someone goes out here and puts the cigarette out of it, and you're in trouble. There we go. Okay. Okay, so hot, good, highly optimized tolerance. Excellent. I mean, if nothing else, a great bit of framing. Then we're going to sock self-organized criticality, and then there'll be a little piece of code because this is hilarious. What is it? It's the acronym there. It's with limited deviations. Anyway, so it's a version of HOT. Okay, so HOT theory. So what is this stuff? So this will go in. All right, so complex systems. So we've talked about these distributions of sizes that we see on what? That make up systems. So somewhat connected to that is if you have these big skew distributions, there are some big pieces in the system. If you get it there, then you really take a chunk out. Especially going to be true for network stories. A lot of these things are built on networks. So we have blackouts, of course we have an example over there, which I don't think anyone, no one was a silly group, don't be group. Is there any story about what happened? Not group people. Does anyone know what happened at all with Super Bowl? I'm sure it's a squirrel. It's a squirrel? The squirrel's okay. Like it. I was actually, so the last big blackout that I enjoyed was, you guys were, do you remember, so the Northeast, you guys were alive 10 years ago? So I was on the last plane that landed in LaGuardia. The pilot, I think, was just determined, I'm going to get us hit. And we land, and no, so that's it, and the tunnel was pitch black, very weird situation. Went back into Manhattan, and it was weird. It was just a weird thing. A lot of people walking up many stairs, and everyone, bad things did not happen. Yeah, it's an interesting business. Okay. Yeah, sleeping in Central Park. Let's see. So disease outbreaks. Yes, another network story. And we've had a lot of models of this. In the last 10 years has been a movement to really understanding, trying to really model what happens with what we have now with the airline system, the airline network, with how people move around. And we can see if you drop in a little patterns over here, how it will spread the models of cities. So that's become much more complicated. You know, it's one of these things where you really try to model the whole system, and it's a bit worrying as to whether you know what you're doing. So again, toy models, modeling the whole thing. Wildfires, obviously a big deal, earthquakes, tsunamis, all systems. So the system's holding together for a long time. You know, Earth is sitting here, it's fine, because the crust is all holding together, and then kapoosh, you know, that thing's happening. So it's exciting. So, but mainly what you see, I mean, as we're sitting here talking about it, for example, I mean, we are complex systems ourselves, and we manage to stay at the same temperature mostly, and do other things that keep us aspiring. So that's a pretty good example of robustness. Now and then things happen. So most of these systems we're interested in because we see them and we're part of them. Is that the biggest feature is that they last, right? That they're robust. And now and then, catastrophic failure happens. And there's great questions. Can you predict this? We're still a bit unsure, I think, about the blackout in 2003 or 4. We're still arguments was this thing, completely short. And then there's this connection in here, this HOT theory that suggests that there's a parallel story involved robustness and failure. And the two are connected. The Okay. So a good word here, and I'll have it on the next slide, I guess, is robust, or good framing as well. We have highly optimized tolerance, which we'll get to. But robust yet fragile. Right? So there's an Achilles heel to the system. That's our classic mythological story. You know, for some reason, I don't know, just dip it in and hold the ankle. You could, the one-time thing, I don't know, just hold the other ankle, back in. Anyway, so that's a good example of robust yet fragile. Of course, it happened a couple of times, but disappointing. They really had a hard time, but they managed to build a big thing here. We're gunning for it ourselves, of course, right? But hasn't happened. One thing unwinds the whole business. All right, so there's our emblem for the day. Obviously not predicted by the, and you can see, right, there's a lot of hubris actually, as everybody's seen. It was never going to happen, but it did. Okay, nice. Okay, so robustness, so systems, of course, there's complex systems. A couple of big reasons that they just simply come into being and have robustness, which is inherently entwined, is simply evolutionary processes, right? So natural things going on. And then design, engineering, we make. And usually once systems become big enough, then there's a bit of everything involved. And so we design the power grid sort of, right? So we design it locally very well, then we connect it up for all sorts of other reasons. And the local things weren't built with the big picture in mind. Boeing, right? Boeing, for example, right now. Lots of different cooks in the kitchen there. But there are many companies involved, 30, 40 companies involved, which was a business decision. Right? Well, it was just cheap to make it cheaper. Of course, it was much more expensive in the end. So instead of building within Boeing, they just spread it out. And that just became a very hard coordination problem. And then you have people arguing for the next big thing. Boeing knows all about this kind of failure too. I mean, they build things that are great, and then they cross some design threshold. The other day, the next, you make the next version faster or bigger or whatever, and you feel like you're scaling it up, but you're also moving across some design border, and you're in trouble. Okay, so here's the idea behind highly optimized tolerance. Spoiler systems, for whatever reason, I mean, arguably it could have come. This will apply to both of these scenarios. Somehow there's been some kind of optimization through natural selection. It's not going to be a perfect optimization. There's going to be some refinement or some testing of the system over and over as it grows or builds. And there's uncertainty, so there's a threat in the system. So the lightning strike is the threat, it's the uncertainty, it's probabilistic, it's inherently stochastic. So highly optimized tolerance. So it's highly optimized, but tolerant and intolerant. And robust yet fragile is the real catchphrase here that you can stick in your head. So people behind this, so Gene Carlson, who's a physicist at Santa Barbara, and John Doyle, who's at Caltech. John Doyle will be I'm going to call him the Han Solo of the academic world. So this guy is pretty funny. So he had okay, let me show you this one. This is his first journal paper. This is an abstract from his first paper that I'm taking. So there's a title. That's Doyle 78. So here it is, basic paper. Guaranteed, whatever, it comes from control theory. Guaranteed margins for LQG regulators. Abstract, they're So that's a start to his academic publishing career, and I think it's So at some point he had the world record for human-powered vehicles. You know, you put someone in an egg and make them ride a bike or become a bike as fast as they can. He was at Berkeley. And, he's a good giraffe, but I don't think he's good by his own image. And preference matters. Yeah, they said we're doing this, and yeah, I think he had the furthest distance. Probably not going to put any more, but he got the little legs. So he's an interesting character, very, very funny. So he runs around saying it's all about this, and he has many other good ideas. Very enjoyable if you ever get to see this film talk. All right, John Doyle. So he's not on. So what we have, so these are the claims. We're going to have high performance. They're going to perform well, right? They're not just some random thing they're going to cobble together. They're going to do a good job. So in terms of the, also, I should have my other graph here, but the forest fire story, most of the time they won't be any forest fires, right? That's what you want. That's the performance there. And it's been designed, built it, not necessarily fantastically cleverly, you don't know the answers straight away, it's iterative, you keep constructing things. But you're responding to the environment, which has some uncertainty. It's not just a uniform uncertainty, it's important that it has some variation, but not extreme. It has some variation. There are more lightning strikes over here than over here on average, but not 10 million times. Right? But if there are changes, if just through chance, or if the environment changes, you're in a lot of trouble with this. Changes significantly, you get in a lot of trouble. Someone puts a lightning rod over in that place. Igor puts one out there. That's what they do. Then you're in a lot of trouble. Someone builds a castle. So equals have this. Right. So highly specialized low entropy configuration. So that's important. So if we went back to our crazy thing. So let's keep this going. There's a lot of randomness in this, right? There's a lot of randomness. Eventually, yes, it will all be one color, but that's a pretty featureless thing. Even in these, so even when there are all these clusters of many different sizes, it's still a bit of a glue. You wouldn't want this to be your, if this was your, if the blue was the forest here and the green was where you remove trees, you're in trouble. So this is a percolating thing. You drop your match over here and it goes up. So it's totally, there's no design, it's a lot of randomness. So this is basically John Doyle versus Tobak. Tobak is no longer around. Unfortunately, died a year. But they had these two different stories. Highly optimized tolerance versus self-organized group, which comes further back in time. Okay. Parallel distributions appear. Of course. That's what we love them, so we want them to be able to pop out. But this is not an obvious thing. This is, some good words here. This is something that's absolutely surprising. All right, so a couple of things we've seen already. So variable transformation, just that simple variable transformation story where we had the sort of thing about the TARDIS and so on. But we were just doing benign transformation variables using one variable that's distributed, whatever it's eventually Gaussian. It's not bad, but it's not uniform. It's not in any way bad. And we have some inverse power relationship with another variable, and that one turns out to have parallel distribution. And constraint optimization. We have a bunch more so those things are still pop up in. Key one is that first one, but all right. So we have these things. There's some transformation between variables. Please load, power law in, power law out. That's not happening here, but this is just a structural thing. We're not putting in a distribution, statistical distribution into power law in its tail. Mild in, wild out. That's okay. My work is good. That's what you want. Right? Because this is not surprising. This is surprising. You never use these words. Okay, so, right, so this is characteristic size varies. Alright, let's get through this example so we can understand. And this is, one contrived example. So we have a square n by n grid. Obviously, this is not what Forrest said. And we're going to have this, I was doing a calculation before, so it has that kind of feel. We're going to put a tree in there with probably a row. Slide together so there's no tree, so nothing burns through that. And then this is some representation of the uncertainty of the environment. So there's some distribution, piece of ij, there's an ij representing the coordinates here, that gives you a probability of a fire start. Right? And this is going to be a mild distribution, but uneven. So fire is going to spread from tree to tree, nearest neighbor. So it's just going to be this guy's on fire, and that will only go these 4 ways. There's another tree here. The squirrels jump out, scamper away, and get caught in electrical wires over here. And everyone's sad because they were watching a game before. That could be what happened. I don't know what's saying it did. Okay, so if you have a connected cluster, it all goes up, right? And there's no, it will happen over time. It basically you're letting it go. These empty sites are blocking that. So this is what we'd like to do. We have some limited energy that we can expend in building fire breaks. You have to maintain it, right? Think about that. There's some hand waving stuff in. But we want to put those fire breaks into, and we don't want to cut all those trees down. We want to, because that will stop our fires. We want to, right? This is where the constraints really matter. Right? That's where engineers can go horribly wrong. So, solve your problem. No more forest fires. Very good car plan. Build fire breaks to maximize average number of trees left intact given one spot. So on average, right? So you're going to test this thing over and over again. Somewhat strangely, you're going to have the forest, drop a spark in, see how big that burn is, and measure the amount of trees left. And then put everything back together, and then do it again. So it's a pyromaniac's dream, played out on a computer. Okay. And so this is going to be a strange way to do it, but we're going to build our forest by adding one tree. This is you can start with the forest and then put in the fire. We'll do it that way. And so it's n by n, and here's the little, so it's a nice little game. We're going to test, this will be the design parameter. We'll test D ways of adding one tree. So we've got your forest so far, and it's an n by n grid, and then you put a tree down in a new place, and you test it. You just take your matches out, and light it all up, put it together, and light it all up. And that's going to be the design parameter. So D is n squared, wow, then you're going to test everything. So you can make a full comparison. That's going to take a long time. And of course, we're just talking about a two-dimensional system here, right? If you have higher dimensional things, 3, 4, social kind of things, crazy. I'm not saying we're putting it, that's a settle. All right, so D equals the design parameter. And we will average over this spark probability for each configuration we test. So this is essentially a random addition. Right? We don't get any testing. Just D equals 1. You pick a site, you still test it, you run all your fires, but you've only got just to keep the algorithm there. But that's it. D equals 2, put it down, choose a random use place to put your tree, test it, and then you choose another place, test that, and then take the best one. Alright. Okay, and n squared, as I said, we test all possibilities. That's exciting. And we want to measure the average amount or the total number of trees left, average area if you like. So there are two things playing off here. Of course, right, we want to again, protects against having no trees. So we want to look at this. So we have, this is a distribution of fire sizes. So FFC is going to be a distribution of fire sizes, which is going to be the cost. So we set up our forest at some point as we're building it. We run all these tests on it. We get some distribution for the kinds of forest fires that can run. And then the yield will be the density of trees that you started with minus the average cost, or the average fire size. So this is the, so it's a density, right? So this is going to be the density of trees that you start with at this particular point in your design cycle, minus what you see to be the average cost, which is the average density of trees removed. And you want this yield to be as high as possible. So here's an example, and I think this is connected to one of them. There's a whole slew of papers about this, but this is connected to one of them, which I must have decided back there probably. So we'll make this a Gaussian of sorts. Yep. And so it's going to have, is the Gaussian sitting in here with I plus A over B. So then it is this. So here is a tree, trees, we've got checkerboard, trees. These guys everywhere. And we have our opposite matches over here because we're line it up. Okay. And then, so the idea is, so if this is I, this is J, then there's this kind of a Gaussian sitting along here. It actually decays, well, depending on the standard deviation, it decays pretty quickly. And this way is this as well. So it's I plus A actually. So I'm going to make it, A could be negative, but let's just, it has a Gaussian decay. This is looking like e to the minus x squared over b squared I, proportional is, and there's a e to the minus, that's an I, sorry. I this way, e to the minus j squared over bj squared. So this is a standard deviation, is these b's. The idea is that it's they're different, right? So there's an asymmetry as well, on top of the fact that there's an asymmetry as keep going up this way. Right? So more lightning structures here. This is where we want to see these guys, right? Okay, good. So there's more width in the y direction if this is the j direction. Oh, okay. How are we doing with that? Just an example. It's not a big deal. The idea is there's asymmetry. Okay, so let's figure these things out. This is quite a good example. Very small, n equals 64, so 64 by 64. And here are four possible choices. There are four examples that have been run here. So d equals 1. So again, that's just a random choice for your next tree. You do run the test, but essentially you're just randomly allocating trees. D equals 2 means you're making a little bit of a choice. You've got to pick two random locations and you take the best one. So it's better. D equals n. Well, it's n squared is the total, so n is relatively a small number of places to check. N squared is where you're doing the whole thing. Make sense? Not how you win. Okay. So these examples here are all the ones that have the best yield. Right? So they don't have the same number of trees in them because they've been grown to the point at which adding more trees starts to reduce your yield. So yield again is what's the expected number of trees that you think you'll have after these fires have been run on average. So if you start to add more trees to this random case, so we will just randomly choose one of these black spots and fill it in, you're just making a bigger mess. You've added one more tree, but you've on average, created, you would be losing, on average, more than one tree in your fires from then on, from that point on. You can imagine it crossing a really bad threshold, a critical point where you add another tree and suddenly you've got a percolating cluster and really bad things happen. Now you're losing tons of your trees. It really drops off. This one is the same. There's no benefit to adding more trees anymore. You can see that this is a very clumsy design process here. It's pretty dopey. It's only choosing 2 each time. Then it's created, let's see, it's created a little border here, or left a little border here that actually goes up here. It's broken here, but it's left here. So that's gonna, and then there's a little pocket in there, I think, and there's a tiny pocket there. But mostly there's a big one, a small one, a small one. So that's protecting against, this is the dangerous point, right? So this is Gaussian distribution pulling up this way, backward. So it's managed to create fire breaks that way. And you've been able to put a lot more trees now than just simply randomly allocated. When you're choosing N, so many more comparisons, really stepped up, then you start to see a much more clearer, just looks much more designed. Clearly much more designed. Very low entropy state. High entropy, messy. You could change this around. We could jumble these points around and visually to us. We could run the whole thing again and get different patterns. We wouldn't really distinguish them. This one, very different to this, right? There aren't so many. You could tweak these guys a little bit, move them around, and say, okay, that's pretty similar. But you can't change it dramatically. It's a low entropy state. And so it does a good job because it's created this border here. There's so what's going to happen is if there's a spark out here, you're out there with your matches and you're running around, then boom, this whole thing goes up. So that's what you've given up there, which is not really true in this guy, but bad things happen. If you started here, you get all of this. This would go through eventually to there. So there's some sealing up, but it's just a bad story. So again, that's true here, it's true here. All of this goes up. If you get anything in here, any spark in here, boom, the whole thing goes up. If you hit any tree. So, it's a nice example. So, optimized fires are great. They do very well, right? This particular example. You can see this is a dimensional story, right? This is a one-dimensional thing that you put in a two-dimensional thing. Right? So there's a 2D story here, and it's 2 dimensions. The structure you're adding to it is one-dimensional. These borders are one-dimensional. They'll have to play out again and again, even with information signals, where you have borders within these sort of one-dimensional string of numbers that would imagine the borders being two-dimensional. So there are, this technique approaches for that. This approach works for that as well. So, but rare events, disaster. Total disaster, right? You lose well over half of the forest. So robustness, fragility. Okay. So then the game becomes, well, this seems like something that human and natural systems could produce, right? And not just forest fire, whichever thing. Seems like a reasonable state to get to. The stat mech story gives you these sorts of things. It's not the features. So, I want to see that. See that here. Alright. So, this is the yield story. Let's figure this one out. This is the density row across here. And so you're adding, in this design process, you're trying to add more trees to increase your overall initial density and testing it. So what happens with that random case is you get up close to what is your percolation threshold. You get up close to it, and adding more trees on average starts to be a bad thing. So they're all, so the d equals 1, the d equals 2 cases here. It's actually very good. D equals n and d equals n squared are up here. So there's an extra story in here that 2 does a pretty good job. It makes kind of an ugly looking forest. It's an ugly looking thing, so So you don't really see the design in it, but it does a pretty good job functionally. Here's the point where it starts to fall off. Right? So this is where you start. So the pictures on the previous slide are from here for d equals 2, here for d equals 1, or the maximum, and here for d equals n squared. Right. And so all of them have to go to 0. Right? If you keep going, designing, if you keep adding trees, eventually you fill the whole thing up. So they all have to go to 0. But you can get a tremendously long way up towards, almost all the way up to the fraction being 1, and having the forest on average do a really good job. Now I'm going to explode. But if you just gave someone and said, on average, after forest fires, this is our yield for trees. But at this point, you say, okay, we have 98% of this area is covered by forest, and on average, we lose 0% essentially. We lose none of it. When it does hit in that big area, everything goes. So it's one of those nasty statistics. It's a parallel distribution. You're not showing it, but the average is smaller, but the variation is enormous. We should at least report the variance. Okay, so that's good. We don't have to worry about the other one. Yeah? So this is a pretty ridiculous graph. This is actually, so there's 20 orders of magnitude here, just to put on the same plot. So it's a lot, so these slopes are hard to see. But these are the, this should be the complementary cumulative for the sizes of these files. And so they're all following parallels. So that's what's emerged. Again, the distribution, the uncertainty distribution going in, Gaussian, notice this, wild, and we're getting the behavior of the system really wild coming in. So this is a big thing. So I've said these things, we just give a few slides. We'll go through some analysis. We'll start that on Tuesday. But d equals 1, as I said, this is pure percolation. We're randomly adding trees below this critical density, which just looks like static, really. You don't see anything. No fires really spread, right, because the trees are all isolated. There's some small drops, but they're not really big. Once you get to this percolating threshold, you can see it. You'll see the forest space. You'll see it, and you'll see a big clump. Once you go beyond that threshold, you start to see one big clump. So if it hits that, you're in trouble. And here's the, as we were saying before, only at that threshold, only at that critical point, where you've added just exactly the right number of trees to start to see a macroscopic forest, do you get parallel distribution of trees of little forest sizes, clump sizes, cluster sizes. If it's a random forest, it's featureless, we only get it there. For the hot approach, you get it for all, you get it for this wide range of parameter space. It's not just one special one. So it's much more, to use it's better robust, like the theory is robust, okay, right? It has there's nothing, you're not going for some really special point. I was hoping that somehow magically you end up at that special point. There's a big wide range of parameter space where things are kind of, that's often what you hope for in these 20 models, right? You don't want to be too outrageously affected by changing inner parameters. All right, so this is good. We'll finish with this nutshell. So they're highly structured. You get this parallel distribution of tree sizes for all densities greater than the percolating cluster, percolating threshold density. It's no longer special. It's no longer something special about whatever 60% of tree, the forest being full. Mostly you have a tolerant story. It's fine to have this uncertainty. Really bad things can happen now and then. It's true. And that's something to really think about. The cold story, we will about that. As long as you're well characterized and the environment is not changing, even non-stochastic, it's not changing in terms of distribution, you're okay. But if you built this system with a poor understanding, you know, if you had this thing back to front, right, you just had you turned the thing upside down, something had a little force this way, you get your matrix upside down or something, then total disaster. Okay, so that's an intro to highly optimized tolerance, and we'll go through some analysis Tuesday.